Okay, this is a review to help you with your physics final. The physics final is going to be broken up into two parts. One of them is basically ideas and definitions, but it's done in an objective format. It is open notes, open book, so you can probably find this stuff, but it will be a timed final, so you don't have forever to do that. And this will be more at the beginning. Those of you who get kicked out of the test before I open it up again, I will go back and grade the parts that you've already done because that happens to a couple people each test. So what I thought I would do is go through the objective part, and then we'll talk about what will be on the test. Basically, the final is going to cover three main sections. It is going to cover, it's going to go back and it's going to deal with waves and optics. That was the first unit in this semester. And then we will deal with electricity and magnetism, although primarily electricity. And then we will do a little bit on universal gravitation. We haven't had a test on universal gravitation, so it'll be on here. So those are the three sections, and that's because that's really the way this semester is put together. Very little in terms of the total amount on the universal gravitation, because we just haven't spent that much time with it. So what I've done is I've put up on the board a bunch of different terms. It's these terms that you should understand well enough so that when you start taking the test, you can look and you can understand what they are. So I'm not going to write these down. You can just snap a picture of this, look these up on your own, whatever you want to do. But we started out when we talked about waves. A wave is a continuing disturbance in a medium. Just thought of that. That ought to be one of the words that's here. And so we have a mechanical and electromagnetic. That has to do with the medium that it goes through. Mechanical needs a medium. Electromagnetic does not need a medium but can use a medium. Different types of wave. Transverse wave, that's a wave where the wave is going, well, I'll do it this way, and the wave is vibrating this way or this way. It's vibrating perpendicular to the motion of the wave. That's when you took your slinkies and went back and forth like this. Longitudinal wave is a wave which, if the wave is heading this way, the wave is vibrating back and forth. Sound wave is a good example of a longitudinal wave. Some terms that deal with the wave itself. Frequency, the number of waves that pass a point every second. The period, the time it takes for one full wave to go. These are always reciprocals of each other. Period is 1 over f. F is 1 over period. The unit is either the second or 1 over second, which is called hertz. Amplitude, how far the wave moves from where it would be if it was quiescent or quiet. So a wave that goes up, that's the amplitude, comes down, should be the same amplitude down here. Velocity is a frequency times wavelength, and I just realized I forgot wavelength on here too. A wavelength is the distance between successive points on the same wave. Reflection is when waves bounce off of a new medium and return, and there are less rigid and more rigid. So if it hits a less rigid boundary, it comes back erect. If it hits a more rigid boundary, there's a reflection that comes back inverted. So those would be the different types of reflection. Refraction is the bending of waves when it enters a new medium. Diffraction is when we have the bending of waves around an obstacle or an opening or an aperture. Standing waves are caused when you have a wave, equal and opposite waves going toward each other, and their interference causes that standing wave. Standing wave would have nodes, places where nothing is moving, and you've seen pictures of those, and we've done those ourselves. Interference is whenever two waves hit and superimpose, and we simply add the amplitudes. I should note that there's two types of interference. There's destructive and constructive. And the difference would be constructive interference means the wave has gotten bigger. Destructive interference means the amplitude is actually smaller. Now we move into a medium is what the wave passes through. These words here tend to do more with when we get to optics. I did put up there's concave and convex lenses and mirrors, diverging and converging mirrors. Mirrors, when light goes through a medium, if it goes into a slower medium, it's going to disperse. That's because the different colors of light will go at a different angle. When we start dealing with refraction, when we deal with light, we have something called N, which is the index of refraction. The larger N is, the slower light goes, and the more the colors of light will be dispersed. You may remember that every color of light has its own index of refraction. They're all very close, but that's why light spreads out in a prism. A critical angle occurs when light is trying to go from a fast medium to a slow medium. No, slow medium to a fast medium, and the angle gets larger, and eventually it's at 90 degrees and it bounces back in. The critical angle is when the angle of refraction is 90 degrees. And by the way, we'll talk about the equation. So there's an equation for that, but that's the definition. Critical angle is the angle at which light no longer, or a wave can no longer leave a medium, a slow medium, and go into a fast one. Real and virtual images would be images which are either actually recreated by the rays of light, or that are what our mind perceives. And you may remember that whole idea that our eye tries to recreate where something is coming from by assuming that light travels to us in straight lines. And so a virtual image is an image that our mind recreates. A real image is an image that's actually there. So that would be that first part. Then we have universal gravitation. And literally all I've done with universal gravitation is list the different men that were responsible for something. I thought about putting Kepler's first, second, and third law in there, but basically you can have that. Of course, you could have this down too. It's really an interesting thing. The first part of the test, this part, I almost thought about not putting on, and I thought, well, it'll bump your grades up a little bit if you're ready for it, if you've put the time in. Newton is famous for the universal law of gravitation. He discovered it. He actually worked it out mathematically, but I would say he discovered the universal law of gravitation. Kepler is the one who analyzed the orbits of the planets, figured out that they were elliptical, and that we have this amazing constant between the radiuses and the period. Ptolemy is known for the geocentric or Earth-centered view of the universe. By the way, Ptolemy did not create that. He proposed it, but actually Ptolemy is more like a historian who put together all sorts of other people's work, but he was also a good mathematician. Copernicus is known for sun-centered. Tycho Brahe is famous for his incredible ability to analyze or take proper measurements. Einstein is the one who said, really, to be honest, that Newton is wrong. It's not a force which is holding the universe together. It's that things that are massive in terms of gravity, actually any gravity, but especially massive things, actually warp space. And as a result, to our eye, there's a force that's pulling them together. And we may talk about that a little bit more. So these are the important people. He's also known, of course, for his theory of relativity. When we get to electricity and magnetism, basically just know your terms. Voltage is the work that can be done on a charge. And that's one of the harder ideas for students to get across. I've mentioned that many times. But voltage is not Voltage is not work that's being done, but if I have a charge and I have a voltage, that charge is going to move. And the work that it does in moving, that charge is how we'd figure out what voltage is. So, although I wasn't going to do this, but voltage is the work that can be done per charge. Current, when there is a voltage and there are electrons, there will be a current. By the way, that's important. The fact you have electrons doesn't mean you have a current. We can have static electricity. That's what that big Van de Graaff generator was. We put all sorts of electrons on there. They can't move anywhere. They're stuck. But if there's a voltage and if there are electrons and there's a place for the electrons to flow, you'll have current. So current is a flow of electricity. Resistance is the natural property where electrons trying to flow are going to have trouble flowing through something. Even a very highly conductive metal has atoms that those electrons are running into, and that would be the resistance. I forgot to put up on here power. Power is the rate at doing work, and for us, it's always measured in watts. By the way, you should know the unit of each. Voltage is V for the unit and V for the symbol in the equation. Current, the unit is amp, and the symbol is I. Resistance, the unit is the ohm, and the symbol is R. Power is watts, and capital P, and energy is measured in joules or in kilowatt hours. And it is an E when we do it, or sometimes a Q. But I think in your book it was always E. The unit of charge power is the rate at doing work. And so when you take and get this equation, P is equal to VI, because that's voltage is joules per coulomb, and current is coulombs per second, and it gives you joules per second. That's what power is. And then you should know what a coulomb is. Coulomb is the standard unit of charge. Maybe I should mention that. Coulomb is the standard unit of charge, and it is 6.25 times 10 to the 18 electrons. The fundamental unit of charge, the smallest charge we have, is the charge on an electron. So the standard unit of charge is this. The fundamental, or elementary, sometimes called, fundamental unit of charge is 1.6 times 10 to the negative 19 coulombs, which is the charge on one electron or one proton. All right. You should know the links between electricity and magnetism. They're called the right-hand rules. I'm not going to ask you to define the right-hand rules, and on a test like this, it's very difficult for me because it's going to be a Schoology test. Very, very difficult for me to have you even draw it. I wish I could, but I just can't. But what we have is a wire with a current flowing through it. It has an electrical field, a magnetic field around it. That's your first link. Second link is that if I coil that wire, I make an electromagnet. The third link is that if I have a current flowing in a magnetic field, that current, that wire will feel a push, and we're going to have a force on the wire. And then the fourth link is when we turn it around backwards, and that is that if I move a wire that is connected, it's a closed loop of wire, we would say, perpendicular to a magnetic field, you will have a current flow in that wire. And we had a number of other terms. We had EMF, which actually stands for electromotive force, but it is not a force. It's actually the voltage that comes from a generator. A generator is taking a coil of wire, spinning it in a magnetic field, and because we're spinning it, and then we have a commutator at the end, the current keeps changing direction. You saw the video on that, I hope. And that's called an alternating generator, and what it produces is called an EMF. And when it does that, there are two parts to it. There's a maximum voltage and current and an effective voltage and current. And then the last little piece there is that we can take something called a transformer, and a transformer is used to transfer voltage and current. One of the important ideas is that the power of a transformer, if it's an ideal transformer, is the same going in and going out. And that's where our equations come from. Power in the primary is power in the secondary. So VPIP is equal to VSIS. And because of that, we can do that. But what we find is, you go back to that fourth link between electricity and magnetism. If I have more turns, I have longer length. And if I have longer length, then I have if I have longer length, I would have more turns, longer length, higher voltage. So by changing the number of turns, I can change the amount. So we'll do the equations in the next video. I kind of got sidetracked there, but that's an overall view of sort of that. I should mention there is something about color. You may remember that white light is all the colors. Black light is the absence of color. And if you take something which is red, it's red because in white light, the red light is bouncing off of it or reflecting. It's not really reflecting, it's being absorbed and reabsorbed as red. If there's no red light, then you're not going to end up with red light coming back off. So if I had something that was, say, blue, but it was in blue light, it would look blue to me. If it was in white light, it would look white. But if it was in red light, it would look black. And so there may be a question on the test about color as well, because we had spent time with that. I won't have the primary and secondary colors and that type of thing on there.